Hi, everyone. Look at our previous example and take 30 seconds to answer these three questions. Look at these 5 complex zeros. In particular, look at these two, the negative I root 3 and the I root 3. How are these two complex zeros related? Second, why does it make sense that we have 5 complex zeros here? And number 3, describe these factors in X when we factor over C. The answer is right in your face. Go ahead and answer these 3 questions, and we're going to extend these later on. Take 30 seconds. All right, how are negative I root 3 and I root 3 related? They form a pair of complex conjugates. And in general, this is true, that if a complex number is a 0 for a polynomial function with real coefficients and all that, then its complex conjugate will also be a complex 0. For example, look over here. When we looked at x squared plus 9, its two zeros, 3i and negative 3i, formed a pair of complex conjugates. When we looked at this cutie, this quadratic trinomial, its zeros formed a pair of complex conjugates. In general, we have this theorem, the complex conjugate pairs theorem. So if f of x is a polynomial with only real coefficients, then a complex number z, say a plus bi, is a 0 of f of x if and only if its complex conjugate z bar, or a minus bi, is also a 0 of f of x. So over here, if we know that I root 3 is a complex 0 for a polynomial function with real coefficients, we know that its complex conjugate partner, negative I root 3, must also be a complex 0. Bear in mind that the complex conjugate of a real number is itself. So if root 2 is a complex 0, then root 2 is a complex 0. We're not saying anything extra, but it does not contradict the theorem. If z is a complex 0, then so is z bar. Well, the complex conjugate of a real number is itself anyway. Okay, so this pattern is true in general for all polynomials with real coefficients. Now, number 2, why does it make sense that we have 5 complex zeros? Well, it's because the original polynomial is 5th degree. It has degree 5. And that takes us to what's called the fundamental theorem of algebra. This is in part 2 of my notes. By the way, in green, I discussed the fundamental theorem of arithmetic and also of calculus. But the fundamental theorem of algebra says that if f of x is a non-constant nth degree polynomial, etc., in descending powers with real coefficients, then it must have exactly n complex zeros. So, for example, since we have a 5th degree polynomial with real coefficients in this nice form, there must be 5 complex zeros, some of which may be real. Remember, complex numbers include real numbers. The zeros may or may not be real, and the zeros may be repeated based on their multiplicities. So, for example, a double root or double zero is counted twice. A double root or a double zero is a 0 of multiplicity 2, and it will be counted twice. A 0 of multiplicity 3 will be counted 3 times, and so forth. So zeros are counted according to their multiplicities. For example, if you have something like x minus 2 all to the 10th, then 2 would count 10 times. 2 is a 0 of multiplicity 10, and the 10 complex zeros are all named 2. But there's only one distinct complex zero. 2 is the only distinct complex zero, but in general, it's a zero of multiplicity 10. I'll put that note down here. So again, for x minus 2 all to the 10th, 2 is the only distinct complex zero, the only different one. There's only one distinct one. There are no others. But if you go beyond the distinct issue, there are 10 complex zeros. They're all named 2. 2 is a zero of multiplicity 10. Likewise, for x to the 100th, 0 is a zero of multiplicity 100. Third, describe these factors in x where we factor over c. I'm referring to this factorization over here. I have it right here. We have here a product of 5 linear factors. Bear in mind that if the leading coefficient were not 1, then we would have that leading coefficient in front over here. So we could have a constant factor as well. The linear factorization theorem, the LFT. If f of x is a non-constant polynomial in ascending powers with real coefficients, and let's say it's nth degree, then it must have a factorization into linear factors over c of this form. So basically, when you factor this nice polynomial over c, you get this form for the factorization called LFT form. All right. So again, f of x equals, well, whatever the leading coefficient is, you could put it here. Here, the leading coefficient was 1, so we didn't write it down. But if the leading coefficient were 2, 3, -6, whatever, then the leading coefficient would go here. Of course, it's a real non-zero number. And then you would write down these linear factors, which are all of the form x minus a complex zero of the function. Remember, a fifth degree polynomial of this type will have 5 complex zeros. And the factors can be listed out as x minus the first zero. There's no order, but you can pick the order. X minus the first zero, and then x minus the second zero, and so forth. And last, x minus the last zero. So over here, again, you can pick the order. If the first zero is 0, we have x minus 0, or just x, as our first linear factor. Since this is a 0, that's a factor. Since that's a 0, that's a factor. Since that's a 0, that's a factor. Since that's a 0, that's a factor. The factor theorem is related to this. And again, if you have copies of the same 0, if you have a 0 of multiplicity more than 1, they can put exponents like squares and cubes and so forth. So for example, for x to the 100th, you can think of 100 copies of x minus 0. But I'll accept this as LFT form. You don't have to write all this out. Now let's do another example of LFT form. So let f of x be x to the 5th minus 8x to the 4th plus 16x cubed. First of all, let's factor out the GCF. The GCF is x cubed. And then when we factor, we divide. The other factor is x squared minus 8x plus 16. The exponents go down by 3. Now, x cubed is still there, but notice x squared minus 8x plus 16 is a nice PST, a perfect square trinomial, which can be factored as the square of x minus 4. Now, if you want to be a real stickler and stick to the form, you could write this factorization as the leading coefficient 1 times, well, x can be written as x minus 0, Since the x is cubed, we could write that 3 times. We have x minus 0, and then do 2 more copies. So x cubed could be written like this if you really wanted to fit the form precisely. And then the square of x minus 4, well, the square of x minus 4. We have 2 copies of x minus 4. So if you really wanted to stick to this Lft form here, you could write it like this. But if I wanted Lft form, then I would accept this as Lft form. X cubed times the square of x minus 4. So this polynomial has 5 zeros. Their names are 0, 0, 0, 4, and 4. There are only 2 distinct zeros, 0 and 4. 0 is a 0 of multiplicity 3. 4 is a 0 of multiplicity 2, because 0 counts 3 times and 4 is counted twice. Remember when we factored our old friend here, 4x cubed minus 5x squared minus 7x plus 2, we put this factored form in Lft form. The linear factors over here, x minus a 0, x minus a 0, x minus a 0, and the leading coefficient was over here, the 4. You need that leading coefficient there. Otherwise, if you were to multiply these things out, the leading term would be x cubed, not 4x cubed. You need the leading coefficient here in order to rescale this thing properly, so that 4x cubed is the leading term, and these other terms are also appropriate. You need this 4 to rescale this. A final note, how is factoring over R different from factoring over C? Well, sometimes when you're factoring over R, you can get stuck on these prime or irreducible quadratics over the reals. So, for example, in our example up here, when we had x to the 5th plus x cubed minus 6x, when we factored over R, the reals, way up here, remember, we got stuck at the x squared plus 3. The leading coefficient was 1, and these other factors were linear, but we got stuck at the x squared plus 3. If we're factoring over the reals, we're sometimes not able to break up some quadratics, namely the quadratics that are prime or irreducible over the reals. A prime or irreducible quadratic over the reals. We get stuck there sometimes. But if you're allowed to factor over C, then even guys like these eventually have to break down. And it did. So what's one reason why we like C? Because when we have C, we can get a nice form for the factorization, the Lft form for the factorization, where we have maybe a constant and a bunch of linear factors, which can clearly indicate the zeros, the complex zeros. Okay, next up, Descartes' rule of signs. This is another rule that allows us to try to figure out information about the kinds of zeros that we have.